Alright, recording has started, and let's connect. Good morning. I'm going to take you to, like always, the practice quiz for today. Problem number 1. If f of 4 is 7 and f prime of 4 is 3, approximate f of 4.002.
Did you start the recording?
I did. Today I started it before, but thank you for the reminder. I need that reminder usually. Does anybody need more time on problem number 1? Alright, so I'm going to draw a rough sketch. I know it goes through this point. How does it go through this point? Well, the slope is 3, so it's kind of steep as it goes through this point. So 4.002, I should be a little bit larger. So I'm going to say that this is approximately the previous value 7 plus, now every time it goes 1 unit right, it should go up 3, but it's going far less than 1 unit. If it went a full unit, it would catch a full 3. How much of 1 unit does it go? 0.002 of 1 unit does it go, so this is going to be 7.006 here. Okay, give me some feedback on this. Still need more practice on this, or you all set with this? I can keep providing more practice if you need that, so just let me know. Alright, number 2, find all critical and inflection points of this crazy looking function that doesn't have any numbers in it. So, the answer of course won't have numbers, won't have very many numbers in it, but you'll get an answer in terms of letters. So, I'm going to give you time with number 2. Okay, anybody need more time with this one? Alright, so what's the process that we use to find a critical point? You take the derivative, you set the derivative equal to 0, and then you solve for x. Now, this we should recognize for two reasons. Negative b over 2a, see this is a parabola, and the vertex of any parabola is this formula. The x-coordinate is negative b over 2a, and then you find the y-coordinate by just plugging that in for the x into the function. Okay, so we could remember it that way. We could also remember it from the quadratic formula. This is, remember, quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. It's everything in the quadratic formula except the plus or minus and the square root stuff. Alright, so that's the critical point. And we only need to give the x-coordinate. I could plug that in and give the y-coordinate, but this is fine. If the a, notice if the a is negative, we're going to get a downward parabola, and so on. Okay. Now, to get the inflection point, you do the second derivative. And the first derivative was here. If I take one more derivative with respect to x, the b goes away, and all I'm left with is 2a. Okay. So, how do you find the inflection point? You try to set the second derivative to 0 and solve for x. But this will have no solution, because there's no x. So there's no inflection point. But what do we already know about parabolas? That if the a is negative, then it's a downward parabola, and that would be called concave down. If the a is negative, f prime prime will also be negative for the entire region, for all values of x, so that would be concave down. And if a is positive, it's a concave up parabola, and that would also be consistent when the second derivative is positive, we get concave up. Alright, give me feedback on number 2. Was this uncomfortable for you because of all the variables? And did you get it, or are you still kind of not understanding it? And give me a little feedback here on number 2. Alright, number 3. Here are some formulas. I want you to write formula for the circumference of a circle. What basic fact do you need about a circle that goes into the formula of the circumference? Same with the area, same with the volume of a cylinder. Cylinder is like a Coke can. And then the volume of a cone. A cone is like an ice cream cone, 3-dimensional. And if on any of these you just cannot remember, I want you to make your very best guess, and it'll really tell you something when you look at your guess as far as, I had this part right. I need to remember it's this, and so on. Just let me give you a couple minutes here. Alright, anybody need more time? Let's go for the circumference of a circle. If I picture a circle, all I need is the radius r. And the circumference, if I extended this all the way across, I have the diameter. It turns out that if you take a rope that goes across a circle, and then you anchor one end of it here, and then just drape it around the outside edge, you'll get about a third of the way. A little bit short of a third of the way around the circle. Do it again, you'll get about 2/3 of the way. Do it again, you get almost back. You need a little bit more than 3 of those. So it's the diameter times, the circumference is diameter times pi, or 2 pi r. Replace diameter with twice the radius. Area of this circle. If you have a circle, and this is r right here, notice that if I took r squared, I get a little bit too much area. And if I take 4 of these r squareds, I'm really close. But I get a little bit too much area. You don't need 4. You need 3.14. And then, when we compare these two formulas, this makes it really easy to remember. The right-hand side have the same 3 symbols. There's a 2 and a pi and a r, a 2, a pi and a r. Same 3 symbols in both. And the units, if it was feet, this would be feet and this would be square feet. And so, of course, the one with the square is the area. Right? Volume of a cylinder. Okay, it's like a Coke can. And we need the radius, r, and we need the height, h. Okay. If you take the base of your Coke can and you try to find its area, that's pi r squared. That's the area of the base. But the area of the base is also the height well, is also the volume of the first layer, because its height would be 1. If that was 1 unit high, then the volume of this would be the same as the area of that base. And now how many of those layers do you have? You have each of those layers. Volume is pi r squared h. Okay, and then the volume of a cone, you can put a cone right inside a cylinder. And then it would be right inside here. And it turns out that you can make 3 of those cones with the volume that you have from the cylinder. So this one is volume is, if you have the full cone, you just take 1/3 of it. Pi r squared h. So same as the volume of the cylinder, except we can make 3 cones. If you think of a gallon jug of ice cream, if it comes in a cylinder like this, and you wanted to make huge ice cream cones that have the same height as your cylinder, you have enough ice cream in there to make 3 such cones. Alright, give me feedback on this. This will be important feedback for me. I don't always review these formulas in a calculus class, and if there are certain ones especially that were helpful for you to review, or that you needed to review, that'd be good to know, and then I'll make sure I continue to do that in other calculus classes. Okay. Let's go to number 4. So it's an integral, definite integral, but before doing the definite integral, I need you to, I need you to draw a picture, estimate the area under the curve. Does anybody need more time on this one? We'll look at it. Now it may be that you can do this integral, but you're not sure what this picture thing is about. Let's do the picture first. We need the function 2x minus 1 between 1 and 2. Now, when I plug in 1, so x, 2x minus 1 to the fourth, because that's the function. When I plug in 1, I'm going to get 2 minus 1, which is 1, 1 to the fourth is 1. When I plug in 2, I'm going to get 4 minus 1, which is 3. 3 to the fourth, which is 9 times 9, or 81. Alright, so I got to go up to 81, and way down. I'm going to exaggerate. The 1 should be even lower, but I want to be able to see the difference. So it's from here to here. It's a part of a fourth degree function, so it's going to be swooping like this. Okay, and like a parabola does, or a fourth degree is kind of similar in shape to a parabola, just steeper. Right. And when we find this integral, we're finding the exact area under this curve. And we're going to estimate it. Now, it's probably not, if I use the average between 1 and 81, halfway in between. Well, how do I find halfway in between 1 and 81? I add them together and divide by 2. 81 and 1 makes 82, divided by 2 is 41. Now, if I use 41, that would be kind of using this as the average height, and I know 41 is an overestimate because this curve's underneath that, but you know, I'll just knock down the 41 a tiny bit. I'm going to say it's so let me get a different color here. I'm just going to say, yeah, maybe it's something like this. And it's going to be, I'm going to estimate the area by what would be the area of the rectangle if I stuffed it down in there. Width times the height of the rectangle. And the width is 1, 2 minus 1, and then the height, well, maybe it's 30 or something. We'll just, if it was a straight line between the two, I'd go with the halfway point. But I can adjust it a little bit for that, so I'm going to say 30. My estimate will be 30. All right. Now let's actually do it. The integral from 1 to 2, 2x minus 1 to the fourth dx. I need a u. If this is just x to the fourth, I would just get x to the fifth over 5. But it's a function of x, so I have to do this u substitution that we learned last time. Du dx is 2, so du equals 2 dx, and this is going to equal, I'm going to change it, so this is u to the fourth, and then dx, 1/2 du. So notice this had to match that exactly over here. So I got, and the 1/2 I'm going to put out in front, and the du I'm going to put here. Now these were really x values. They're not written in, but that's what they are. They match this letter. And so we need to change to u values. This will be the quick way to do this one. When x is 1, u is going to be 2 minus 1. It's going to still be 1. When x is 2, I'm going to get 4 minus 1, which is 3. So then I'm going to get u to the 5th over 5. The over 5 and the 1/2 will combine to be 1/10. And I'll evaluate that from u equal 1 to u equals 3. And I'm going to get 1/10. I'm going to get 3 to the 5th minus 1. Because 1 to the 5th is still 1. And then when I do 3 to the 5th, I'll punch that out of my calculator. 243 minus 1, 242. So it's 242 over 10. Which is 24.2. And what had I estimated? I was a little bit high. In my picture it does kind of look a little high. I think I should have gone a little lower, because this area up here won't fill in all of this. 24.2 is the area underneath this curve, 2x minus 1 to the 4th, between 1 and 2. And that's the area right there. Alright, so give me some feedback. Were you able to estimate by drawing the picture? And then also on doing the integral, which part was easier for you? And just overall feedback. Now, many of the homework problems you had to do for today were more complex than this one. And you looked for 2 functions of x. But even in this simple one, you're still ultimately looking for 2 functions of x. Remember, the only thing that you can really integrate, let's go to yet a new color here. You can really only integrate it's got to have the f prime in there. If you don't have the f prime, you cannot do this integral. Now, this one, what were the 2 functions of f? The f and the f prime. Well, the f was 2x minus 1, a first degree polynomial. And the f prime then was just 2, which is a 0th degree polynomial. So you still had 2 polynomials the one with the larger degree was the f, the one with the smaller degree was the f prime. You need two functions that one is the derivative of the other to be able to, if you have function within a function, to be able to do it with the u substitution. And, alright, number 5. Find the average value of x squared on the interval 1 to 3. Alright, anybody need more time on this? So, a little picture. F of x equals x squared is a parabola. At 1, it's a height of 1. At 3, it's a height of 9. And between here and here, what's the average height? Well, we know the average height is almost halfway between 1 and 9, but if we pick exactly the halfway point between 1 and 9, which would be 1 plus 9 is 10, divided by 2 is 5. If we picked 5, that would be the halfway point if it was a straight line connecting these two. But this is underneath that straight line, so it's going to be smaller than 5. Now, to find the average value, the exact average value, you have to have calculus. No other way that I know of to do this. So the average for f over that interval is going to be the integral from 1 to 3 x squared dx. Now when I do that, that gets me this area underneath that section of f. But that's not the average value. If I then divide it by the width of that rectangle, I must be then getting the height that I would need to get all of this area in that blue rectangle to be the same as the area underneath the curve. So this becomes x cubed over 3, evaluated from 1 to 3, divided by 2. And that's the same as factor out the 1/3, 3 cubed minus 1 cubed over 2. It's 27 minus 1, so it's 26 over 3 divided by 2 over 1. Invert and multiply. 26 over 3 times 1 half, which is 13 over 3, which is 4 and 1/3. Now, does that look reasonable according to my picture? Sure, a little bit smaller than 5, 4 1/3. Got it. All right. Quick feedback on average value. And questions on homework? No questions on homework? Alright. Then we can go to the next section. Intro to optimization problems. Alright, and you're going to need to be working in your groups, and this is 4.7, so we were just at 5.5, so we're going back and picking up this one section in the book. And optimization problems is a really, really common use of calculus.
Do you mean 4.5?
Pardon?
Did you mean 4.5?
Oh, it is 4.5.
Because 4.7 is the Hopdall's rule.
Yes, okay. 4.5, thank you. It's 4.5, and I haven't even defined what an optimization problem is, but we'll see that as we work through this problem. So, a farmer with 750 feet of fencing wants to enclose a rectangular area and then divide it into 4 pens with fencing parallel to one of the sides, maximizing the area. We'll explore this problem. So, part 1. Draw a rectangle and then insert more fencing parallel to one of the sides. So, figure out what in the world does that mean. Draw the picture for it. Communicate with each other in your group, and I'll call on a group in a minute. So, let me ask group 3. How do I mend this picture? How do I draw insert fencing parallel to one of the sides? How did you do it?
Well, wouldn't you divide the rectangle into 4 equal pieces?
Like, oops, kind of like this? 4 equal pieces?
No, because it says parallel to one of the sides. So it would have to be either horizontal or vertical
Which
from,
one did you do?
well, I tried doing it horizontally and that's not enough area. So, well, I guess it didn't matter, but I did it vertically because it looks bigger.
Ah, okay. And you're going to be maximizing the area. So, how many vertical lines do I need to make?
Oh, well, you need 4 pens, so you need 3 lines.
Okay, where should I draw the first vertical line?
About and halfway,
Halfway?
yeah, I think. No, let me
Okay.
see. Um,
And then the next one?
and then halfway from the first
Okay, cut
mark.
this portion in half and then cut this one in half.
Yeah.
Okay. Alright. That seems pretty reasonable. Now, I'm going to do this number 2. Draw this same outer rectangle again. This time insert more fencing parallel to one of the sides in a rather different manner. Alright, so to do it in a rather different manner, I would have to do it this was my original rectangle. Parallel to one of the sides would have to be doing the same kind of idea. Cut it in half, cut each of these in half. Like this. Insert fencing parallel to one of the sides in a rather different manner. Okay. Let's go to number 3. If you're going to use exactly 750 feet of fencing, which of your 2 diagrams would be more efficient use of material and contain more internal area for 750 feet? Well, Kylie was already saying it was the vertical ones. Because this one you're using way too much fencing. You're going to have to make it rather short. You can probably make this outer rectangle a lot wider. Yeah, because you're using a short amount of fencing to make the barriers. Alright. So the answer for this would be number 1. Alright. Number 4. Suppose you want to enclose the maximum amount of area with your 750 feet of fencing. Predict which of these diagrams, A, B, or C, will be the shape that contains the maximum possible area. Now I'm giving you 3 choices. And so I'm going to send you to your groups and then you kind of figure out as a group which A, B, or C you choose. So you'll have to come to consensus. Alright, so one way to do this is to make the outer rectangle a square. So instead of making this outer rectangle rather rectangular-like, it's square. Another way to do it is to make the 4 inner rectangles all squares. Like this. And a third way to do it is there are no squares involved. And I mean, this is just one possibility, but none of these will be squares. Alright, so those are your choices, A, B, or C. consult. Which do you think the correct answer is going to turn out to be? So I'm going to call on each group. We'll record the answers, and I'll give you 10 more seconds. All right, group 6, A, B, or C?
We said B.
Okay, 1 for B. Group 4.
We're going with either B or C.
Suppose you had to go with one of them. Which one would you go with?
B.
B. Group 3. And group 2.
I think we went with B.
And group 2.
See, no one was in my group today.
Okay.
But I mean, I'm gonna say feels like B, but I'm not certain.
Everybody was going for B. All right. Maybe it kind of looks, because of the appearance of this, that doesn't look so good, and but maybe it is. Maybe it's all going to be squares. That looks kind of reasonable, and squares often show up. Like, for instance, if you were going to make a general fence that's occupying the most area, and you had to make all the edges straight, it would be a square. If you're going to make a general area and occupy the most area, but the edges don't have to be straight, it would be a circle. So squares and circles show up a lot when we maximize things. By the way, the nature of this problem is it says, what is the farmer wanting to do? With 750 feet to fence, divide it into 4 pens, here's the main thing. He's trying to maximize the area. When he's maximizing or minimizing something, that's what we call an optimization problem. Yeah. And so let's go to, so that's what our votes were. And then let's go to part 5 now. Part 5C is the model we will use and label, and it is the most general case. We can use part 5C as our diagram, and it helps us to remember, like if you use this as your diagram, you might be tempted to call this side X and this side also X, because they look equal, but they don't have to be equal. It's better to use this, and that kind of reminds you, if you're calling this side X, call this side Y, make them two different things, and it could turn out to be that X and Y are equal. It doesn't prohibit this from happening, but when you call them different letters, it allows them to be different. If you called them X and X, then they have to be the same. So we have to use the most general case. The outer or inner rectangles may or may not be squares. We label the edges below. So I'm going to say, instead of labeling it below, I'm going to come up here and label it. And I'm going to label it with, hang on a second. I want to be consistent with we could label any of them in any way, but we'll call this x, and then this is x again, x again, x again, x again, and we have a choice. We can take one of these from here to here and call it y, or we could take this whole distance from here to here, call it y. It doesn't matter. We'll solve the problem either way. But I'll choose to do it like this. All right. Now, write the equation that the variables x and y must satisfy. To do that, you have to look back at the original problem, how it stated. What did it tell you must be true about when you make this region? And make an equation that involves x and y that must be satisfied. So let me give you a minute and I'll call on a group here.
Are we trying to, I just understand the question clearly, are we trying to maximize the area within the 4 pens or the total amount of area?
The original problem is maximizing the total amount of area, which is the sum of the areas of each of the 4 pens. Okay? When you're making an equation right now that involves x and y, that doesn't really have to do with maximizing yet. It's just some condition that x and y must satisfy because of what was stated in the problem. All right, group 4. Do you have an equation that x and y must satisfy?
Are we allowed to pass?
You bet.
We're still okay.
Do you need just more time?
We're just kind of lost because it's kind of abstract for us.
Okay, that'll happen in plenty of these problems. They are pretty abstract. Let me try group 6. Do you have anything?
We do not, so we're also going to have to pass.
Okay. Let me go to group 2. You got anything?
And we're looking again for the fencing around, correct?
Yeah, these x's
Okay,
and the y's in the fence.
Okay, so I had, well, the first one I had was 2x plus 2y equals 750.
You're
For 1?
really close. Let's write it out. You put 2x plus 2y equals 750. So what you are saying with this equation is...
Oh, I forgot the internal ones. I was.
Ah, yes. Very good. Good you
So
spotted that. What you're saying is you got to use 750 feet of fencing. Exactly. That's what he has. He has 750 feet of fencing. And so all these regions have to be 750 feet. So, Francis, if you're going to change your equation, what would you change?
I'd add 3 more, so 5x plus 2y.
Oh, very good. So we count up all the x's. There are 5 of them. And then there's 2 of these y's. 5x plus 2y has to be 750 feet of fencing. Any questions? Yeah. Now we're going to complete this table below. If x is 70, what does y have to be? Well, they have to satisfy this equation, so you can figure it out. And then look at your picture and get the total area of the enclosed regions, of all 4 regions, you know, the total area. And let me give you a couple minutes to fill out this chart. So you're going to need a calculator.
Like we sprayed, and as we're spraying, bugs are climbing out all over the place of the wood cracks and crevices, you know what I mean?
wow.
So,
Okay,
we.
we're recording right here. Okay, I'll give you a minute more. I'll be back in a moment. So I got 200, 175, 150. So how did I get these numbers? I just plugged in 70 for the x right here and then solved for y. Or I could have just taken this equation in general, moved the 5x to the other side, divided by 2, and then plug the x in, come up with each of these. So as the x gets bigger, of course the y's got to get smaller. And then 125.
So I didn't realize I just totally did a completely different. I thought you were telling us to substitute or to have the x being 5x. So I divided it by 5 and multiplied it by 2. So I got totally different
X.
answers. So I didn't really understand
Okay.
what she wanted.
Okay, gotcha, gotcha. Does this make sense now, though?
You're saying when x is 70
Mm-hmm. If
to
we
put
put,
70 for x.
that's right. And then the equation up here would look like 5 times 70 plus 2y equals 750. And this is 350. Subtract 350 from both sides. And that's
And then
400.
divide by 2.
Divided by 2, y is 2.
Okay.
And
So
that's what I did with each one
that
of
way.
these. Okay,
Okay, that makes sense.
okay. And then the total area of the enclosed, if we look at this region, how do I get the total area? Do I multiply y times 5x or just y times 1x to get the total area? From the picture, I'd be tempted to multiply y times 5x. But when I really think about it, all you need for the area of the big rectangle, ignore all the x's in between, is the outer dimensions. So it's just the x times the y. So you just multiply these two things together. 7 times 2 is 14. And then you're going to have 3 zeros. So it's 14,000. And when you multiply these two together, you also get 14,000. And you multiply these two together, you get 13,500. You multiply those last two together, we just get 12,500. Just adds 2 zeros to it. Alright, everybody okay with this?
Yes?
Alright, so let me give you a minute with number 8. Analyze the table. What values of x and y appear to give the maximum possible area, and what is this maximum possible area? And you might pick numbers that are actually on the table, or you might do some deductive reasoning and pick some number that's actually not quite on the table, but you can kind of figure out. So think about it, come up with an answer. I'm going to call in a group in a minute here for number 8. And then we'll take a break. All right, let me go back to group 4 again. Any ideas?
We said that the maximum, well, the values that are giving off the most maximum area are going to be 70 and 200 and 80 and 175. And then the total area would be the total maximum area would be 14,000.
All right, so you're going to give me 2 answers for this, and that looks very reasonable from looking at the table. So the x is 70 and the y is 200, and then also x 80, y 175. That seems very reasonable. If you had to give just one answer though,
I would say maybe it would be the first one, the 70 and the 200, but that's just a guess.
okay? Now, would one of these have any preference over the other? Well, if they're both going to give you the same total area and his objective was to maximize his area, no, we wouldn't prefer one to the other. But suppose we had the line of thinking that maybe the maximum area doesn't really show up on this chart. But maybe we could reason our way to the maximum area, in the dimensions that produce the maximum area, from this chart. Anybody have any ideas on that line of thinking?
I noticed that when I plugged it in, it almost acted as a downward parabola. And then I put a value in between 70 and 80 and I got a higher value.
I got even the highest. So if we put in something, what number did you put in between 70 and 80?
75.
If you put in 75, very good observation. You noticed you were getting some shape that looked like a downward parabola if you graph this stuff. And when you put in 75, what was your total area?
It should be 28,125.
I got 14,000 and
Oh yeah, that sounds more
62.5.
reasonable. I think I did it wrong.
I think so. 14,000 what?
62.5.
A little bit higher than either one of these, if in fact we're getting some shape that's kind of a downward parabola. And because of the symmetry, you'd go halfway in between these. So all of these are insightful answers. I like taking both answers. That would be my initial instinct too. And then when I really thought about it, if I had that insight of, oh, maybe it's kind of like a downward parabola, maybe the high point is going to be halfway between. So we have our strong suspicion that maybe this is the dimension. Now if that's 75, we still have to figure out what y is, and so on. And let's stop at this point and take a break. So we will start again. At 12:57. See you in a bit. at 6:30 on Thursday, comma, done. What do you say, Pepper? Yeah. All right, we're going to start up again. And all right, the problems that we're going to see in this section might well look like the one that we looked at. And in a typical calculus class, you only get the explanation that I'm about to give you right now, which is the calculus way to do the problem. And the difficulty with that is that many students have trouble understanding just what the problem was about and really understanding the basics of it. And then they're shown this fancy calculus method of solving the problem. So we investigated the problem and we got to an answer of 75 might be our best estimate. By the way, if the x was 75, what was the y? Brianna, did you wind up coming up with the y in that case?
That one was 187.5.
187.5. So
Yeah, and
let's,
I actually kind of solved it by accident earlier when we were doing
Yeah.
number 1.
you solved it by accident, yeah?
Yeah, because I just took the whole amount of fencing and divided it by 4,
Okay.
and it gives me 187.5.
So this is 1/4 of the fencing
Yes.
for the y, and so that's interesting. 750 divided by 4 gives us the 187.5. Now, that being the case, with our picture, 1/4 of it is across the top, 1/4 of it is across here, and then the other half of it has to be, so half of the fencing is used horizontally and half is used vertically. And if this is the correct answer, let's look back. Everybody had picked option B, thinking the inner rectangles were all squares. But according to the picture then, this x would be 75, and the 1/4 of 187.5, 187.5 divided by 4 is 46.875. And so they are not they are not squares. So it's not this shape. It looks like it's going to be non-squares if this indeed was the correct answer. And let's look at the calculus way that we would work out this problem. So let me shift over to my camera. So we have our picture. Cut it in half, cut each of these in half for the 4 regions. We call this X. Calling all of this Y. Alright. So in a more formal sense, for a calculus way to solve these problems, there are, let me give you some general overview. In any optimization problem, what it means to be an optimization problem is to find the min or max of something. And sometimes problems are a bit of both. For instance, if you were sending a rocket ship off to Mars, when you're designing the rocket ship, it might be that the exterior, the very exterior of the rocket ship is very, very expensive material. Because, you know, it has to withstand some, you know, going in and out of the atmosphere and maybe take some punishment and still be very durable. So, on the one hand, you might be minimizing the surface area. So you have less of this very expensive outer shell. And then on the other hand, you might be maximizing the volume so that you can put the maximum amount of material you can in there for, you know, testing everything you want to while you're going to Mars. So some problems are a mixture of these kind of things. The one that we had, and all the ones that we'll be looking at, are just a simple one thing. You're going to be minimizing or maximizing something. All right. So when you're optimizing, you first of all, you state what you're doing. So number one, what are we doing? We are maximizing, not minimizing, and the area, and we'll call it a variable A. So state what you're doing in terms of minimizing or maximizing. The second thing, in each one of these problems, you'll be having some given information. And we state what is given in the form of an equation. And that was the equation that we came up with, 5x plus 2y. We had 750 feet of fencing. So that was the constraint that we had to work under. And if this is the way we're going to shape it, then clearly 5x plus 2y has to be 750. All right. Then the next thing is after you just get comfortable. And I'll tell you, when I was in school, the problems that I enjoyed the most were the problems that were in context, like this. And the reason why I did well at these and really enjoyed them had to do, one of the crucial reasons was, whereas my other fellow classmates would tend to want to jump right into the calculus, the equation, and they'd say, show me the shortest possible way to do these, I would play around with the problem and just start to understand what it meant. So all the things that we did today in this, which were like drawing the picture, and then making a table and kind of seeing, well, what makes sense as far as, you know, what might a possible value of x be, what might a possible value of y be, what might the area in each case be, all that kind of stuff. I draw pictures, make tables, do whatever till I just feel like I intuitively understand the problem. If I didn't get to that place where I intuitively understood what was going on, I wasn't going to start the problem. I just, you know, if somebody was trying to show me a solution, I'd ignore them. I would just play around with the this and that and try different x's and y's out until I'm then ready to start to go to something more. All right. Now, 4. Optimization equation. Now, the optimization equation has to start with the variable that you're trying to maximize or minimize. A equals. And from this, we say, all right, my area of the total fence, well, it's on the, I don't need all these internal x's. I don't even need these lines across this. The area is just x times y, way out here. And that's what I need to maximize A right here. Now what's going to happen in each one of these problems is that you're going to have a difficulty. So the problem is this. You have two variables on the right-hand side. We only know how to optimize if there's one. If it was A in terms of x or A in terms of y. But if it's A in terms of x and y, we can't do it. So we get past this problem. So we're going to get that almost every time in all these kind of different problems. Is there's three variables, two input variables and one output variable. And we have to get it down to one input variable, one output variable. How do I do that? Well, I use this equation up here. I'm going to solve for y. You could solve for x either. Just solve for one of the letters. So I'll have 2y equals 750 minus 5x. Divide by 2. 750 divided by 2 is 375 minus 5 halves x. Alright, now what will happen is every time I see the y over here, I replace that. So the given constraint gets incorporated into this. X 375 minus 5 x. Now, what I think is going to happen here is I think the answer I'm going to get is going to be that x is 75. Because that reasoning seemed pretty solid. So, but how do I get to x is 75 from this kind of crazy equation right here? Well, let's multiply it out. Now I have resolved this problem. There were two variables on the right-hand side. Now there's only one variable on the right-hand side. Don't think of this as an A. Think of it as a Y for a minute. Because this is just one variable and another variable. We're kind of used to X and Y's. If you think of it as a Y, what's the shape of this graph? It's a downward parabola. Because the x squared is a negative coefficient. And the area will have a highest point, and it'll be wind up being at the top of that parabola. Right over here. Now, if I want to maximize A, and it's in terms of one letter, x, I can, the quickest way to find it is take the derivative, set to 0. To find critical points. If it's going to have a max or a min, and if that max or min is not going to be an endpoint, then it'll be a critical point. And so this will zoom us right in on that. Alright, so let me take a picture here. Alright, so I'm going to leave the original picture, leave this equation, alright, so I'm going to get dA dx, I take its derivative, I get 375, minus, and when I take the derivative here, the 2's cancel out, minus 5x. Now, by the way, this isn't the only way to solve this. Since this turned out to be a parabola, a downward parabola, I could just use the vertex formula of a parabola and come out with the highest point. But calculus gets me to the same place very quickly. And then I replace this with 0, bring this over, divide by 5, and 75 is what I'm going to get. Just what I suspected I was going to get. And then I had 5x plus 2y is 750. So I'm going to plug in that 75 in there, and then that'll lead me to y is equal to, what was it, 187.5, I think. Okay, and so now we have to come back to the original question to make sure that we're answering the original question. Okay. He wants to enclose a rectangular area and divide it into 4 pens. We'll explore the problem. Alright, so basically he wanted to know what were the dimensions of the sets. So we're going to tell him to make the outer region 175 or 75 feet by 187.5 feet, and then place these equally spaced throughout. And we do get a non-rectangular region. And let's go back. When we had taken guesses that they were all squares, perhaps the guess would have been a little different, because it turned out that the x was larger than the y, the smaller portions of the y. These were 75 and these were about 46. So if I had drawn this one more so that these were longer than those. Maybe that would have made more sense, that we would have come out with non-square regions internally for this. Alright, so that is the basic setup for how we would do an optimization problem. Let me take a picture. picture of this. Any questions? All right, because I'm going to go on to a new problem. It'll look very different from this. There can be tons of different kind of, anytime you're trying to maximize or minimize something, that's where calculus really comes in handy. Because the maximum and minimum points turn out to be tops of hills, bottoms of valleys. And those are critical points. So all you do is get the derivative, set it to 0. Alright. So let's do this problem. Find two numbers whose product is negative 16 and the sum of whose squares is a minimum. Alright, so before we start into this problem, your task is to figure out what in the hell is this thing asking me to do, and see if you can just play around. Remember how we kind of explored with playing around, drawing pictures, making tables, and so on. Do this individually, and then consult in your groups, and then I'll ask a group. So let me give you a few minutes with this problem, because this is, I think, the hardest part of the problem. Just interpreting the English into, what am I really being asked to do? Okay, let me ask group 6. What's this asking?
I haven't discussed it with my group yet, but I'm pretty sure that it's asking. Well, first of all, two numbers when a plus b is equal to -16, and then but whatever combination, because there's a lot of possibilities for that. So whatever combination of two numbers, you can get the lowest point out of. I don't know how to explain this. Uh, so when a squared plus b squared is equal to the minimum amount possible compared to other
Okay,
options.
I like your explanation. So give me an example.
I don't know if I really have an example, but
You were talking about A and B. What's one possibility that A could be?
a could be like -8, and b could also be like -8. Or,
Now, it's saying whose product, not whose sum.
oh, sorry. Yeah. So then that could be 2. B could be 2.
B would be 2. Okay? And then if A is -8 and B is 2, then what are we looking for?
The sum of these squares to be the lowest point possible.
Right. And what is the sum of their squares then?
Going to be 68.
A squared plus B squared, 64 plus 4, 68. Nice. All right. Once you get it into a concrete example, you're ready to make a table. And the table could be very revealing and just kind of get you understanding what's going on. And notice how important the example was too, because we all do that kind of thing that you did, like -8 and -8. When there's something complex going on, there's really easy to get one of the parts misinterpreted. And then, we come back with an example that can help us straighten this out. All right, so we have this. If this is -8, and this is 2, this is 68. Can you give me another one? Another example.
-4 and 4.
-4 and 4. And 16 plus 16 is 32. Sum of their squares. Can you give me one more example?
-1 and 16.
Right. And it doesn't even have to be the case that these are whole numbers. One of them could be square root of 3. And then the other could be the square root of whatever number it has to be. There's nothing in there that says these got to be whole numbers. And then we're going to get 1 plus, now 16 times 16, I think that's 200 and, what is that, 256? And I think 257. Somebody can punch that on the calculator and make sure I'm right, but I think that's the case. Alright, so from what we've written down in our table so far, do you have a guess as what the answer might be? Christian, let me come back to you. What do you think? You have a guess?
Well, so far, -4 and 4 are looking the lowest, but there's not a whole lot of data points on here really to go off of either.
That's right. So, and does that make any sense to you? Or do you think there might be some point in between that might be even lower? Kind of like last time. The optimal one was kind of in between.
I mean, yeah, it does make some sense to me, but if it was me personally, I'd probably want data points pretty close to 4.
I would check out some data points really close to 4 to check it out, and maybe on either side of 4.
Yeah.
And if 4 is really the optimal one, maybe you'd get some kind of symmetry where it'd be, 3.8 and 4.2 might give you the same value. And if they're both a little bit higher than 32, that would give us more information, so on. All right, so anyway, with something like this, we can start to understand what the problem is getting at. All right, now we want to go through the calculus way to get the solution. We're going to suspect, this is my suspected solution, -4 and 4. But and the point of these problems is to do it with a calculus method. If you can do it by this other method, that's not really what we're trying to teach here. We're trying to teach how to set up equations and take derivatives and so on. And I tend to start with really simple problems that could be solved another way, but when you get to the really tough problems, there's not really no other way than to solve it except with calculus. All right, so when we take the steps, let me just review the steps that we did before. I put them up in here. What are we doing? We're maximizing or minimizing something. And then we were stating what was given. Now, we did the get comfortable part. So oftentimes the get comfortable part is even done before. So this order isn't generally, you don't have to follow this order. And then you're going to get the optimization equation. All right, so start with, are we maximizing or minimizing, creating a variable for that, and then state what's given, and then we'll come up with optimization equation. Let me give you a couple minutes to do this stuff, and then I'll show it here as well. Alright, so what am I doing? I'm minimizing, because this is right here. Minimizing sum of squares, which I'm going to call S. S for sum or S for squares, whatever I want. Okay. Then, what was my given? Two numbers had to multiply to be -16. We can call them A and B, like we were setting up here. You can call them X and Y. It doesn't matter. generally speaking, the convention in math, though, is A and B we tend to use as constants, things that are fixed and can't vary, and we want to look at this more as a variable. So I might have a slight preference for x and y, but wouldn't mean that A and B is wrong. It's just going against the kind of convention. So x times y is equal to negative 16. And then this was the making sense of it. So then the fourth part was the optimization equation. We have to start with this letter. It's the sum of the squares. The x squared and the y squared. Any questions up to here? This was a lot. Is there any parts of this that are fuzzy that you want me to review again? Alright, so when we get to here, we are at the same problem that we were at last time. One output variable, but two input variables. We don't know how to take the derivative when there's two input variables. We're going to have to get only one input variable. How do we get from two input variables down to one input variable? Exactly what we did over here before. We solve for y. Y is equal to negative 16 divided by x, or x to the negative 1. So I'm going to replace that in here. Every time I see this y, I replace it with that. Now, why did I choose, instead of putting it over x, to call it x to the negative 1? Because I'm eventually going to have to take its derivative. And I like it in this power form, x to a power. So s is equal to x squared. 16 times 16 is 256, I believe. X to the power to power multiply. X to the negative 2. And then we're at the same place that we were at before. We have something that we are trying to, in this case, we're trying to find its minimum, its lowest point. Now the other one was a parabola, which we knew had a highest point. This one, because it has this x to the negative 2 power, I'm not very confident about its shape. But I'm just going to take its derivative. So, to minimize s, take the derivative, set to 0. And let me take a picture. And erase the upper portion, give myself a little space. So ds, dx, 2x, and then if I double that, that's 512. 250, yeah, doubled is 512, x to the minus 3. Okay, and then I'm going to set this to 0. And when I set it to 0, I'm also going to factor out, well, no, I won't. I'm going to put it back to this format. I'm going to move this to this side. And then I'm going to cross multiply. They have to be equal to each other. So 2x to the 4th is going to be 512. Divide both sides by 2. Take the 4th root of both sides. Since it's an even root, I'm taking it both sides. I have to put a plus or minus sign. I get x equals plus or minus 4. And it turns out either one of those is correct. Because when x is positive 4, y is negative 4. Or if x is negative 4, y is positive 4. Either combination works. And so the two numbers. Now here, the one thing that we didn't do is we didn't verify that this is, because when it's a derivative and you set the derivative equal to 0, you get it's a critical point, which is likely a max or min, but it might not even be either one. So the one thing I might want to do is take this function, x squared plus 256x to the negative 2. I want to graph it on Wolfram alpha. And I want to see if when x is plus or minus 4, if we're getting actual minimums of this. Okay, so I'm going to go to Wolfram alpha. X squared plus 256 divided by x squared, or x to the negative 2. And from this perspective of it, we're too close to it to see. From this one, you see it is something that has a minimum at about 4 and another minimum at about negative 4. This blow up here is just this region to this point, to 4. You can't see that it's about to turn its way up right there. Alright, so that confirms. And we've got it. The two numbers are 4 and negative 4. Alright, whenever there's a worded problem, you need to give me a worded answer. Don't give me like x equal 4 and then stop, or x equal 4 and y equals negative 4. Give me a worded answer. Just like if your boss was somebody who didn't understand the math of it, gave you the problem, you put it in a nice simple way that he or she could understand. Alright, the homework is 4.5, and if you look on our schedule, you will see that Tomorrow is set up to be a review day. And the final exam is on Thursday. We won't be doing anything else but the final exam on Thursday. We've been doing a lot of review in the practice quizzes. Tomorrow I'm going to use part of the time to show you a rather complex optimization problem, because some of the problems in this section get very complex, and so it's good for you to see an example of a really complex problem. And then we'll also spend time, if people have questions on some of the homework that was for the review questions, or any other questions that they have, so bring your questions to class tomorrow. We will stop here. Any questions? Everybody understand what's going on?
Mr. Shankin, I have a question. So, for the given, it looks like the. Hold on, sorry, I have to look for it. It looks like the optimization equation that you gave for the previous problem. And I'm kind of confused on. I'm just confused on the part where you did the two equations, and how do you know which one to plug into the other one?
Okay. In both cases, that's a very good question. In both cases, the given condition only had two variables in it. Like look here, x times y equals -16. And the optimization equation has three variables in it. And you're optimizing this while these two get to move, but they don't get to move independently of each other. They're related to each other through this. Okay? And so it's the equation that has only two letters that you solve for one of them in. And then you substitute that into the equation that has three variables in it. And then that becomes a new equation which is two variables, and then we can do our calculus on it to find its maximum or minimum. Okay? And if we compare this to the previous problem, so there again was the given, just has the two variables. This is also sometimes called the constraint equation. That's how x and y are constrained. They have to meet this condition. If you use it more than 750 feet of fence, you can't do the problem. And they're constrained in that way, and then the area is like super general. It's just any x times any y, and you can't even maximize or minimize this unless it is constrained. And then we take the constraint equation, solve it for y, substitute it into the one that had three variables, and go on. Does that clarify it for you?
Yeah.
Okay, good.
So are all these optimization problems going to pretty much follow the same format of A equals XY?
They are going to have a tremendous amount of variety in them. And, but the solution technique, you can kind of follow this. There'll still be a given, there'll still be an optimization equation in each one of them. But there'll be a huge variety of problems. It can be challenging, and I'll give you more insight when we do a more challenging one tomorrow.
Okay, thank you.
You're welcome. Anything else? Okay, I'm going to stop the recording.